Welcome back to another exciting episode of Space Nuts. I'm your host for this season, Heidi Campo, and joining us is Professor Fred Watson, astronomer at large.
Actually, that's quite a nice. It's quite a nice epithet. That it should be Fred Watching, because I watch the universe. Fred Watching, here loud and clear. Looking forward to speaking again, Heidi.
We're off to a great start. No, that is fun. You know, we are all observers in this universe.
Yeah, that's
and
right.
you are listening to Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Today we have some very interesting articles. We're kind of kicking things off. It's kind of a mystery episode. I feel like this is a very, very detective heavy episode. We've got mysteries being solved. We have mysteries unsolved, and we have clues to mysteries. So our first article this week is we are talking about a mystery that might be solved. So this is we're looking at what this is the home address for some missing matter.
Yeah, that's right. It's a story that I find really interesting because the groundwork for this work was laid down 5 years ago here in Australia, with work that's been carried out on something you and I have spoken about before briefly. Briefly is the word because we're talking here about fast radio bursts, which are things that have only been known in the last, it's getting on for 20 years now since the first observations were made, but they're still relatively new in the armory that astronomers can bring to bear on the universe. And what they are is pretty well what the name says. They're bursts of radio radiation. These are detected with radio telescopes, not visible light telescopes. And they are, fast is probably a misnomer. Short would be a better word. But they, because they only last for typically a millisecond, a thousandth of a second, thereabouts roughly. Often they've got structure in them as well, which is interesting. When you look at the profile of the intensity of that millisecond burst spread out, if you can magnify the sort of time domain, you can see that there are features in that, peaks and troughs, squashed into that millisecond. So very, very fascinating objects. Their origin is still not certain. That I think the best guess of my colleagues who work on this kind of thing is that they are flares on magnetars, and magnetars are highly magnetized neutron stars. And these things apparently are able to have flares on their surface, which can be very intense. That these radio bursts are very, very bright in the radio spectrum. So one thing real quick, Fred, I'm sorry. So no worries.
I have noticed, based on the questions lately, that we are getting a lot of new listeners lately. Can you maybe specify to some of our newer listeners the difference between a neutron star and perhaps our star?
I can. Sorry. That's a really good question and a really good point to make. So neutron stars are stars that have reached the end of their life. Their hydrogen fuel, which is what powers stars like our sun, that's being powered by hydrogen fuel as we speak. That fuel has run out on a neutron star. And the stars are really interesting because there's a constant battle going on between the radiation that is coming from these nuclear processes, which is pushing outwards, and gravity, which is pulling inwards and trying to compress a star like the sun. So it achieves a balance between radiation and gravitation. And so you can imagine what would happen if at the end of a star's life, the radiation stops because the nuclear processes have actually changed. They don't stop, but they change. What's going to happen is gravitation wins and compresses the star down. And that sometimes happens explosively in the case of what we call a supernova, an exploding star. And so one possible remnant from such an event is a neutron star, in which the thing has collapsed, and the only thing that's stopping that central core of the X star, the star that is now no longer a star, the only thing that stops it collapsing completely to a black hole is the outward resistance of the neutrons within it. And so those neutrons have an outward pressure, and that limits the collapse. So what you have is a star that used to be perhaps like our sun, 1.3, probably more actually in the case of a neutron star, because they're bigger than the sun. Anyway, 1.32 million kilometers across. Suddenly he's collapsed to something 10 kilometers, 7 miles across, but with incredibly high density, and all sorts of unusual phenomena take place in those stars. They are generally magnetized. Many of them squirt beams of radiation out, and because they're rotating, those beams have this sort of lighthouse effect that we see them flashing. But we believe as well some are so highly magnetized that they form a different species. They're what are called magnetars, and apparently they have flares on them. And these flares are what we think gives rise to fast radio bursts. So that's where the science is. Astronomers have been now observing these fast radio bursts for best part of a decade. And one or two of them repeat, which are a bit mysterious because it suggests that something's rotating, because you get this repeating appearance of the burst. Often, though, they just come out of nowhere. And there are several radio telescopes in the world that are actively looking for these objects. One of them is down here in Australia, the ASCAP, the Australian Square Kilometre Array Pathfinder, and that actually was one of the ones that contributed to the work that was carried out that I mentioned a minute ago, about 5 years ago, in looking at what these fast radio bursts might tell us about not just magnetars, but about the space through which the bursts of radiation travel. Because we now know that most of these radio bursts take place in very distant galaxies. They're galaxies that are, where distances are measured in billions of light years. They're a long, long way off. And so the radio bursts have traveled through a lot of empty space, apparently empty. And so I'm getting near the story here. This is the introduction to the story. We're nearly there. What we find with fast radio bursts is that the bursts are dispersed. That's the technical term, which is a little bit like the way a prism breaks up the light of the sun or a white light into a spectrum of colors. The same sort of thing happens as radio waves travel through space. You've got this spike of radiation, but as it goes through space, this dispersion phenomenon takes place, and the result is that the different frequencies are spread out in time. So, if I remember rightly, I'm not a radio astronomer. The shortwave, the higher frequencies arrive before the lower frequencies. Is that right? I think that's right. Yes, it is. And the high frequencies arrive first, but this burst in different frequencies, it's still a spike of radiation, but you're now looking at almost like you've dispersed it into a spectrum. You're looking at different frequencies. And so the lower frequencies arrive later. Now, that tells you something about the space that the radio waves have been traveling through, because there is what we call the intergalactic medium, and that is basically a very rarefied gas, if you like, although you're talking about 1 atom per cubic meter or thereabouts. It's that sort of rarefaction. But there's enough of it, because you're coming through these great distances. There's enough of that gas to have the effect of dispersing this radiation. So the amount of dispersion tells you how much gas there is that the radio waves have traveled through. And that was the breakthrough made about 5 years ago by a team of Australian scientists led by a fantastic young gentleman called J.P. Marchant. I think it was Jean-Pierre, a wonderful radio astronomer in Western Australia, a young man, 2 weeks after this breakthrough paper had been released, he died. An absolute tragedy, this huge breakthrough.
Terrible.
Yeah, and I think he had a heart attack, if I remember rightly.
It was probably the paper.
Whatever it was it absolutely rocked the Australian astronomical community. This new knowledge that had been created, and he was the lead author on the paper. Sadly, he died. However, that work has now been carried on at other radio astronomy observatories, which brings us to the story today. And this is a paper that has been released by astronomers at the Center for Astrophysics, the Harvard-Smithsonian Center for Astrophysics, CFA. And what they've done is they've taken this work a step further, because they've looked at many, many more fast radio bursts. As you'd expect, these things are coming in and are being constantly observed. And what they've done is they have looked again at the structure or the constituents of the intergalactic medium, the space between the galaxies. And exactly as the Marchant and work proposed 5 years ago, they're able to use this as a measure of just what the contents of the intergalactic medium are, and they find that it is enough to account for what we call the missing matter. Now, this is not dark matter that we're talking about. This is normal matter, protons, electrons, the normal stuff which we are familiar with, which in fact, is only something like 20% of the amount of matter in the universe. The rest of it is the dark matter. That's something else. But even that normal matter that we know about, when we look at the calculations as to what should emerge from the Big Bang, the event in which the universe was formed, we can't find enough of it. That's why we call it the missing matter. But it now turns out that this combined set of researchers looking at the intergalactic medium find that there is enough matter in the intergalactic medium to account for that missing matter. So this is a problem solved, as you said at the beginning. Yeah. The two things absolutely dovetail together. The predicted amount of matter in the universe is now exactly what we find when we include this intergalactic medium. So it's amazing research. It's very fitting that it should be our lead story on this edition of Space Nuts, because, as I said, it's got an Australian content. The thrust has now moved to other observatories, but we have this global picture now of what dark matter can tell us. Sorry, what fast radio bursts can tell us about not dark matter, but the missing matter of the universe.
Oh, that's wonderful. This reminds me when I'm trying to do math unsuccessfully, and I'm trying to find why I can't get the right answer, and I forgot to carry the one. It turns out it was there the whole time. Yes. The answer was right there. I just forgot to grab that one little piece to pull it in to get the correct answer. But they solved such a complex problem, and isn't that kind of funny? Sometimes the answers are right there in plain sight.
Exactly, it's in plain sight. Yeah.
But it's like you said, one atom per. What did you say? It was one
cubic
atom per
meter. That's it's something like that. It's that kind of level. It's a few atoms per cubic meter, perhaps. But yes, it's in plain sight. But you need the thing that's made this possible, this detection possible, is the fact that these bursts of radiation are so short. They're milliseconds, and that means that as they're dispersed into different frequency bands as they pass through the universe, you still can detect this dispersion of the frequency bands. Whereas with a constant radio signal, you wouldn't do that. That you've just got radiation coming all the time. There's nothing to tell you whether the lower frequencies are slower than the faster frequencies. There's nothing to tell you that.
So Fred,
wonderful detective work. Yeah.
Oh yeah, it's fantastic. So by these radio astronomers, then, so they do radio astronomy. What is your specialty in then? If you're not, so I have to make a joke. It's not Space Nuts if there's not a few dad jokes, and I have not been holding up my end of filling Andrew's shoes. So you may not be a radio astronomer, but technically you are an astronomer on the radio.
That's correct. Yeah. I like it. Yes. Your dad jokes will go far, Heidi. So my speciality, and really my work now is in sort of policy and things of that sort, rather than observing. But for 40 years, I guess I was, in fact, more than that, nearly 50 years. I was an optical astronomer, and that means I use telescopes that look at visible light. So giant telescopes that have a very shiny mirror at the base of them. In fact, the one I used principally was the 3.9 meter Anglo-Australian telescope, which we celebrated the 50th birthday on last year.
Oh, good, happy birthday, telescope!
Yes.
0G, and I feel fine.
Space nuts.
So would the ESA's Proba 3 mission, that telescope, would that count as a big mirror telescope?
Yeah, it's a small mirror telescope.
Okay.
But it is an optical telescope. That's right. So it's looking at visible light, and a lovely segue there to the next story, Heidi. So this again, needs a little bit of background to get over its significance. But this, I think, is a fantastic story because it kind of means that you can make an eclipse of the sun anytime you like. As you know, eclipses are rare. In any given place on the Earth, they're a rare phenomenon. That's to say, when the moon exactly blots out the disk of the sun, or blacks it out, that means the moon's shadow on the Earth's surface passes over different places. We call it the path of totality, because that's where you see a total eclipse. And that's only narrow. It's only 50 to 100 kilometers wide. 30 to 60 miles, I guess, something like that. So it's a rare phenomenon at any one place. And that's why when eclipses come along, people chase all over the world. Everybody here in Australia, or certainly in the state I'm in, New South Wales, are looking forward to July 2028, when an eclipse will be seen from this state. And in fact, the moon's shadow will pass directly over Sydney. So Sydney's going to be the centre of the world's astronomers for a short time in 2028. It is already, of course, but in a different sort of way. Anyway, one of the reasons why scientists are so keen on watching eclipses is because when the moon's disk blots out the visible disk of the sun, what you see is the sun's outer atmosphere, its corona. And this is it's a almost ethereal glow around the sun, which has got structure in it that comes from the magnetic field of the sun. That dictates what the corona looks like. There are many mysteries that we don't understand about the corona. One is why its temperature is so high. The sun's surface temperature around 5,500 degrees. This is degrees Celsius. The temperature of the corona, about 15 million degrees. You're talking about this huge difference between the bit that we can see and the bit that is invisible, except when you have an eclipse. That's because it's very faint compared with the disk of the sun. And the mystery is, why is the corona so hot? So the corona, and it's thought to be, we actually think it's all about magnetic fields again. Anyway, the corona is an interesting area of study, but you can't see it unless you're in an eclipse. Now, the problem, you might think, okay, well, why don't we make a telescope with a little disk that blots out the light of the sun so that you can see the corona around it? And there are such telescopes. They're called coronagraphs. That's the name gives away what it's for. They only work where they really only work in a vacuum, because the atmosphere tends to scatter the light and blots out the view of the corona. So one or two very high mountain sites have had coronagraphs used on them. And you can also use them in space, but they have their limitations. And this gets us to the story that you mentioned, Proba 3. This is actually two satellites which are operated by the European Space Agency. And they are about, if I remember rightly, 150 meters apart. They are arranged so that one has a sort of disc. One has got a disc on it. It's disc shaped, if I can put it that way. And if you line that up with the sun, as seen from the other spacecraft, which has a telescope on it, probably with a shiny mirror in there somewhere, that lets you blot out the sun's disk, and it gives you the best view that we have outside a solar eclipse of the solar corona. And the reason why this is in the news at the moment is because we're just starting to see the first images from this Proba 3 mission. It's a European Space Agency mission. And we can see the corona of the sun in great detail, just as we would if we were watching an eclipse from the Earth. And so this is a step forward. It's a new technology. It is going to allow us to monitor the sun's corona in real time and for a long period. I think they're proposing, is it 1,000 hours of observing of the sun? Yes, it will create about 1,000 hours of images over its 2-year mission. And anyone will be able to download the data. So it's a really interesting step forward by the European Space Agency and the scientists who are working on this piece of equipment to let us see the sun's corona over the next 2 years in great detail.
It's fantastic. I'm looking at the images right now, and I've got to say, some of you may get this reference. It looks just like the late 90s, early 2000s Windows Media Player visualizers.
Yes. Yeah.
Doesn't it? It's got such a interesting hue to it. I feel like I could be listening to like early 2000s techno music with these images.
We can probably provide that somewhere.
Some space techno. My other question, since this will be available to the public, would this be a good opportunity for any citizen scientists to tap into? And are there any programs that you know of that people may want to be paying attention to if they are interested in getting involved in citizen science?
Yeah, that's a great question. And, there is a wonderful array of citizen science projects which are related to astronomy. Various ones. The Zooniverse is the sort of, I guess you've probably heard of the Zooniverse, which is a kind of cluster of citizen science projects that brings to bear the resources of our citizen scientists to bear on astronomical data. And you can bet your life that there will be, I don't know particularly that this is the case, but you can bet your life that there will be people poring over these coronagraph images from Proba 3, looking to see what we might discover about the solar corona. It is, I think it's a really, if I can put it this way, it's a project that is ripe for exploitation with citizen science.
Yeah, and I'm such a, you guys have probably heard me talk about citizen science programs on here before, because I'm such a big advocate for everybody getting involved, because don't save it for the brilliant people with the PhDs. We love you, Fred. You're wonderful. But if we can export some of this work to the whole pool of talent, and I've always learned this, the more I get involved in the space industry, is don't be the person to tell yourself, no, I can't do that. Let somebody else tell you. You just start pursuing it. If you're interested in it, get involved. There's so many opportunities and there's so much to learn. We still have more questions than we have answers. So there is absolutely, here's a pun, here's another pun. I've got two for him today. There's space for you. There's space for you to get involved in space. We need your help. So citizen science programs are a fantastic way to get involved. And I think this is a little bit more of my bumpier segue, unless you had something you wanted to say, Fred?
No, I'm just a big fan of citizen science as well. I think it's fabulous what is achieved by that. And I wholeheartedly agree with your comments there, Heidi. But I think you had a nice segue coming up there, which I've probably ruined now.
Oh, no, I think it was going to be a pretty bumpy one, so this is okay. I will say, I do know that actually I remember, because I got some they called it the NASA TOPS program. TOPS
Okay.
standard for something, Open Science Repository, something like that.
Yeah.
But it's just a casual certification that you can get online from. It's an official NASA thing that you can get and just put it on your LinkedIn. But they just talked about a lot of different citizen science programs, and I believe I remember reading, if I read this correctly, a lot of breakthroughs have happened with hurricane technology and early detection of hurricanes through citizen science, because that was one of the first places that we tapped into citizen science. Don't quote me on the decades. I'm terrible at my history, but the first cited use of citizen science was, the former belief was that wind always moved one direction, because if you're standing in the wind, it's coming at you one direction. And this guy was I wish I had his name. I'm so sorry. But he was like, hey, I think wind moves in different patterns. And so what he did is he had a weather event, and he had people posted all over the place. And he's like, tell me which direction the wind was moving. And they reported back to him, and he discovered that, yes, the wind was not always moving one direction. So that was, I don't know if you know more about that story.
I don't know that, but that exactly. It's, it's wonderful when people have an idea like that and manage to muster the resources that he clearly did and get the results. And citizen science is a lot like that.
Okay, we checked all 4 systems and keying with a go.
Space nuts.
Yeah. So here's my bumpy segue to the last article. I guess we can say, if we're keeping it with the detective metaphor for this episode, this is a clue. So we had the first story was we've solved something. The second one is we have I guess the second one was the clue, and this last one is there is a mystery. This is a open case yet to be solved, which is a mysterious link between Earth's magnetism and oxygen. So this is an open mystery. We don't know the answers.
We don't, and it is really quite a significant result, Heidi, that has come from scientists. Actually, one of them is at my alma mater, the University of St Andrews in Scotland, Scotland's oldest university, founded in 1413. I was there shortly afterwards, as I always tell people. It's the University of St Andrews, and also scientists at the University of Leeds. So this is work in the UK. The story is basically that we have this trend that is detectable by techniques that are quite remote from what we do in the world of astronomy. It's what was it? It's biogeochemistry, I think, was one of them. So what scientists have looked at are what you might call proxies, things that tell you about something else. And for example, one of the examples is this. If you look back through the geological record, you can find evidence in the geological strata of periods where there were lots and lots of wildfires, what we call bushfires here in Australia, forest fires elsewhere. So you can find evidence of that. And the scientists are saying that is a proxy for the number of these wildfires is a proxy for the amount of oxygen that was in the atmosphere at the time. Because wildfires spread much more readily if you've got an oxygen-rich atmosphere than they do if you've got less.
So interesting.
Oxygen. Yeah. So it's that kind of work that's been done. Also, something that's a little bit more directly measurable is the history of the Earth's magnetic field. And that's one of the ways that we know that the Earth's magnetic poles reverse probably 3 or 4 times every million years, something like that. So the magnetic field of the Earth is something that we can get from the alignment of grains of crystals in rocks. And that tells you, how well these are aligned, tells you about the intensity of the magnetic field. Excuse me. So this group of scientists, sorry, I've got an oxygen-rich throat at the moment. It's wanting to cough. So these groups of scientists have looked at something that nobody would have expected to correlate, but they find that there is a correlation between, and this is looking back over 500 million years, so they're looking back in time over 500 million years. And when you plot the strength of the Earth's magnetic field over that period and compare it with the amount of oxygen in the Earth's atmosphere over that period, the two graphs match very, very closely. There's clearly a link between the amount of oxygen in the atmosphere, the intensity of the magnetic field. The mystery is that link telling you that more magnetism means more oxygen, or more oxygen means more magnetism, or is it telling you that there is something else going on that affects both the magnetic field and the oxygen as well, and affects them both in the same way? So some of the process that we don't really understand yet. So a really big mystery. But the reason why I'm mentioning this on Space Nuts is that it feeds into our understanding of what might constitute places where life evolves elsewhere in the universe. Because we know most of the oxygen in the Earth's atmosphere actually comes from biological processes. It's what we call a biomarker. Somebody looking at the Earth from outside and seeing that much oxygen, if they have life of the same kind that we have, they could say, yes, that's a biomarker. That is marking the Earth out.
Similar to K218b, right?
Exactly. That's right. Although it was dimethyl sulfide was the biomarker that was caused for the exoplanet K218b, which is still of great interest to astrobiologists. We don't really know, first of all, whether that finding of dimethyl sulfide is real or whether it's being confused with some other molecule, the signature in the spectrum that the James Webb Telescope took. And we don't actually know whether that is genuinely a biomarker in an environment different from the Earth's. So lots of questions attached to that too. But this new finding, the link between magnetism and oxygen, whatever causes it, may be something that will feed into the understanding of the way life processes work by astrobiologists, and perhaps will tell us more about the kinds of places that we might look for extraterrestrial life when we get the next generation of giant telescopes with big shiny mirrors. And the biggest shiny mirror of all is going to be the European Extremely Large Telescope, should come online in 2028. Its mirror is 39 meters in diameter. It's huge. Anyway.
Wow.
Yeah.
Well, I mean, but this is important to consider. This is one of the first things they teach you anytime you go to any kind of STEM related program is, okay, correlation does not mean causation.
Exactly.
And you said this. I mean, it's like, we don't know if it's this, or this. And it's, I mean, I'm looking at the trend lines right now. I mean, they are right there. It's so easy to jump to the conclusion and say, yeah, these are so highly correlated, but then we just have to remind ourselves why, and we don't know. This one's a mystery.
It's a mystery. And, well, I'm sure it will be the focus of a lot of really interesting research over the next year or two. Maybe, Heidi, you and I'll talk about whatever they find in a Space Nuts down the track sometime. But yeah, we should keep an eye on this one because it's a very exciting result.
Well, I think that is a good segue to kick it back to you, our listeners. We've talked about a lot of fun things, questions, answers, solutions, and more questions, and citizen science in there. I think we should just take this time to encourage you guys to stay involved, because you can be a part of these breakthroughs. And then instead of writing in just simple questions here on Space Nuts, you can also say, hey, as a citizen scientist myself, I have discovered this. What do you think about these findings? And I think that would be really neat to hear those kinds of statements from you guys.
Absolutely. We could then tell the world, remember where you heard it first, here on Space Nuts.
What a perfect ending. Fred, this has been such a fun conversation. Thank you so much.
My pleasure always, Heidi, and I look forward to talking to you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.